All right, so what is a hypothesis? Our hypothesis is a tentative prediction of the results of the research. This is what I suspect. That is step one in your 7-step process. Step one is I'm going to make a determination of whether it's going to be a one-tailed or a two-tailed test. So a researcher's tentative prediction of the results of that research. It's formulated on the basis of knowledge of the underlying theory or implications from the literature review. So most people who are going to do a study are going to read the literature review. They're going to find out what's missing or if there are any gaps, or if they want to replicate the study, they formulate based on that knowledge. They test the hypothesis leading to the support of that prediction or fail to support that prediction. A good quantitative hypothesis is based upon sound reasoning. I got to have a significant difference. It's based on numbers. It's based on the data strength, and I'm using the appropriate statistical procedure. Provides a reasonable explanation for the predicted outcome, significant or not significant, clearly and concisely states the expected relationships between the variables if you're doing a correlational test, and is testable. There are a lot of people that want to do studies that are very difficult to obtain data. And it goes back to the credibility and believability aspect of it. If you can't test it, then it doesn't matter what statistical procedure you're going to use because it's going to be inappropriate. All right, types of quantitative hypotheses. Research hypotheses state the expected relationship between two variables. You have what's called a non-directional. No relationship or differences exists between the variables. Now, this goes back to this thing of two-tailed tests. Now, if I'm on a non-directional test, I'm going to be looking at a critical value this way and a critical value this way, because I don't care if the relationship is positive or negative. All I'm interested in is there a significant difference between the two groups. That's non-directional. Don't care if it's a positive. If I'm looking at math scores of 5th grade boys and 5th grade girls, I don't care if the 5th grade girls score higher or lower than the boys. All I'm concerned about is there a significant difference between the two groups. The directional, expected direction of the relationship or difference. So in this case, in a non-directional test, I'm not concerned about positive or negative numbers. But in a directional test, I have to, because my hypothesis is going to state that. I'm going to say that 5th grade boys score significantly higher than 5th grade girls on math tests. So it's one-tailed. It's directional. I have made a direction that they're going to score higher. So in this case, it's over here. And then the null is that there's no statistical relationship or difference exists between the variables. So we have the null hypothesis, then the directional and non-directional tests. And so we'll get into the difference in all of those in just a second. So in a non-directional test, the basic difference here, there's two ways of writing a quantitative hypothesis in statistics. The difference in a non-directional test is you're going to see equal, not equal. Null hypothesis is always as an equal. This group equals this group. Because if they equal the group, there's no difference between the two. Now again, it's not this group is 0 and this group is 0, this is 1, this is 1. Remember that the definition is that the difference is so minute that it doesn't regard any further attention. So in this case, what we're looking at, there's no relationship between mean math attitudes and mean math achievement. So here's two different ways of writing this. This one is u equals 0. The alternative is u not equal 0. So if I reject the null hypothesis, what I'm saying is that there is a significant difference. The two groups aren't equal. If I fail to reject the null hypothesis, I'm assuming that the two groups are equal, that there is no difference, which is what I place. In the alternative, there is no difference in this different way of writing it. There is no difference in mean math achievements of students using technology versus those who do not. This is just another way of writing this. So it's the difference of group 1 and group 2 equals 0. The null hypothesis difference of group 1 and group 2 not equal 0. So the two groups, if I reject the null hypothesis, I'm saying that there is a significant difference between students using technology versus those students who do not. If I fail to reject the null hypothesis, what I'm saying here is that there's no difference. Students who use technology and those who do not have the same scores or similar scores. So that's one way of doing the non-directional test. Now the directional test is written a totally different way. Fifth grade students score significantly higher. Okay, now I've made a commitment that I'm now turning this into a one-tailed test. Now, the direction of the alternative hypothesis corresponds with the direction of what your interest is. So if I'm scoring significantly higher, my alternative hypothesis is going to reflect that. Remember, the null is always equal. So the alternative hypothesis is going to reflect the one-tailed test. And the direction of the arrow points to the end of the distribution of interest. Since I am putting significantly higher, the arrow points to the positive end of the distribution. Now, to make sure that I cover all mathematical possibilities, I go back and I change the null hypothesis to less than or equal to. So that covers all possibilities there. Here, students using technology will score significantly lower on mean anxiety scales than students who do not. So again, the difference between the two, less than points to the left end of the distribution. I'm going to be on the negative side. I have to be concerned with positive and negative numbers. Here, the null hypothesis is always equal to, and I change the top part to make it greater than or equal to make sure I cover all mathematical possibilities. Now, talked about before this thing called a critical value. In every statistical procedure, you're going to have a critical value that you're going to be compared to. You're going to have a critical value and an observed value. The observed value is what you calculate. That's going to be compared to the critical value based upon your alpha level, your sample size, and so forth, and one-tailed or two-tailed test. Once that value is determined, your calculated value is going to be compared to that. And anything that falls at or beyond that critical value, any observed value that falls at or beyond that critical value, is going to lead to rejection of the null hypothesis. So the critical value represents the beginning of the rejection region. So in a two-tailed test, you're going to have two critical values. You're going to have one on the negative end and one on the positive end, and anything the area beyond is going to be rejection of the null hypothesis. That's why I don't care if it's positive or negative numbers. Two-tailed test. Anything that falls in between is called the fail to reject region or the safe region. Then you have the observed value, the calculated value that is compared to the critical value for statistical significance. So I'm going to crunch the data using whatever statistical formula, and I'm going to come up with an observed value, OBS. And if that observed value falls at or beyond the critical region on either end of the distribution, then I'm going to have statistical significance. That's on a two-tailed test. On a one-tailed test, if I'm put that the critical value is going to be significant greater than, higher than, more than, or whatever it is, it's going to be on one end of the distribution. And whatever value I have, the observed value, if it falls out here, it's rejection. If it falls out here, it's failed to reject, regardless of what size of the number is. It could be a negative 1 million. If the critical value is 3, this could be a negative 1 million, doesn't matter. Still fail to reject. Okay? So the observed value is what you calculate compared to the critical value on how it falls. So on a two-tailed test, notice that there's another way of writing this, the alpha divided by 2. This means you divide the alpha level into two parts. So in this case, what you have is you have an established alpha level. Now remember, the alpha level is the percent of times the researcher is willing to commit a type 1 error. So we have an alpha level of 0.05 on a two-tailed test. It's divided by 2. So I have to divide that alpha level, and I get 0.025 on each end of the distribution. Okay? Now, what makes the difference between the two on a one-tailed test, I don't divide the alpha level. The entire alpha level goes on one end of the distribution or the other, which makes it absolutely critical to understand that a one-tailed test is more powerful. Why? Because I'm not splitting the alpha level into two parts. The full alpha level goes on one end or the other. That's what makes an alpha level, the one-tailed test more powerful than a two-tailed test. Years ago, back in the 50s, there was a show called Superman with George Reeves. In one of the episodes, he was in some place in the South American islands or whatever, and he flew down there, and the wicked king or whatever, or prince, decided that he was going to get rid of Superman. He was going to, thwart his plans. So he wound up jailing Superman, and Superman, being the man of word that he was, went into jail. Well, Superman called his science friend who flew down there, and he said, look, I have to prevent this assassination. I have to get out of here, but I can't break out. And the scientist says, well, if you concentrate, you can split yourself into two people. Now, he did that, but he also said that as two people, you're not going to be as powerful as you are as one. So you're not going to be able to, a bullet can affect you and all these things. So he did split himself into two. He wound up having to pull, using his counterpart to pull the jail cell out. He couldn't do it by himself. And once, he also got shot. But once he flew back and became one, then he became the more powerful Superman. So by splitting in two, he was less powerful than he was as one. Same thing here. If I split the alpha level in two, the test becomes less powerful. I have to have more sample size than it is by itself. All right. Whoa, those are neat lines. But see all the difference that you have in the critical value. That's why here, positive and negative numbers, scores are greater than, higher than, more than. Scores are less than, fewer than, shorter than, whatever it is, one way or the other. Here, it's immaterial whether we have positive or negative numbers. All we're looking for is a difference. Now, problem is, if you use a two-tailed test, you can only report a significant difference. You can't report that this group is higher than the other because you didn't test for that. You can only report that there is a significant difference. The only way you can report that there's a significant difference and also it's higher is if you include it in your original step 1 of the 7-step process, and which is, here we go, the 7-step process. Formulate hypothesis. Here we go, the null and the alternative, and indicate a test for difference. Is it directional, non-directional? How are you going to use it? Here's my null hypothesis, here's my alternative, but I have to stipulate whether I'm going to use a one-tailed test or a two-tailed test. Am I looking for a difference or a direction of that difference? Establish an alpha level, allowing for power, effect size, and sample size. Because once I have an alpha level established, that's going to be that determination to commit a type 1 error. 3, determine appropriate sampling distribution. That's going to become a little bit more clear as we go along because we have a certain formula that we have to go through to make sure we have the proper sampling distribution on whatever chart that we're going to use. 4, formulate a decision rule. What this is going to be is going to keep you in track. And it's going to say I'm going to reject the null hypothesis if my if my observed value falls at or beyond the critical value. So it forces me to keep that part in mind. I will reject the null hypothesis if my observed value falls at or beyond the critical value. 5, gather the data and perform appropriate statistical procedure. This is the data crunching. Once I crunch the data, now I'm going into step 6, which is summarize. So I compare the observed value to the critical value. And since my step number 4, I said I will reject if my observed value falls at or beyond the critical value. Now I'm going to summarize. Since my observed value did fall beyond the critical value of whatever it is, I therefore reject the null hypothesis. Or my observed value did not fall at or beyond the critical value of whatever it was, so therefore I failed to reject the null hypothesis. And then 7, draw a logical conclusion from the results, which basically says that since I rejected the null hypothesis, I can conclude that there is a significant relationship between 5th grade math scores of boys and girls, or significant difference, or whatever you're choosing. So your conclusion is going to be based on how you summarize in step 6. So these are the 7 steps that no matter what statistical procedure you use, if you follow those 7 steps, it'll keep you on task. So in summary, remember that hypothesis testing does not prove anything. That is absolutely and probably the most critical thing out of this whole essence of hypothesis testing, is that you're not going to prove anything. You're just going to support or fail to support your hypothesis. And we'll see you in the next module.